the cloud. Um, as we all know, this screen is not awesome. If you're really having trouble seeing, you can sit real close to Damari or Jose and look at that screen. That's okay too. I can check in on my request about the fixing the screen, but I don't think it's going to happen. All right, so chapter 2, as we've expanded our math into the world of integers. And we're going to look at sections 2.3 and 2.4 today. So more math with integers. And as a reminder, our integers are all the whole numbers, 0, 1, 2, 3, 4, etc. And also all the negatives, -1, -2, -3, -4, etc. Zero doesn't have a negative because 0 is just 0. And so far we've been doing addition and subtraction with integers. And that can get really confusing, right? Because if we have like minus a negative, and I had that list of 8 rules that that you kind of have to keep track of. I think multiplication is actually a little bit simpler with integers. So let's do a brief review of multiplication in general. Using whole numbers. And these are sometimes referred to as the positive integers, or non-negative if we include 0. So if I take 2 times 5, I can see that as making a rectangle that's 2 units on one side, 5 units on the other, and then counting all the squares, which is 10 squares. And of course, I could also write it the other way, and I could write it as 5 times 2, which if I want to, I can see as turning that rectangle. So now instead of 2 sets of 5, I have 5 sets of 2, which nevertheless is 10 squares. I like the rectangle way of thinking about it, especially as you're working on building your math. They're called math facts, but where or learning your times tables is what it was told when I was learning it. Because the rectangles can help you with the counting. But another way to think about multiplication is as repeated addition. Multiplication is just repeated addition. So 2 times 5, I can see as 5 plus 5. It's just the addition here. Not a whole lot repeated there, but I could also write it as 5 times 2. And now I can see how multiplication is really just repeated addition. You add 2 to itself 5 times. And either one of those gives you 10. The reason I bring this up is both because the book shows what this looks like on a number line, but also this is helpful when we start multiplying with negative numbers. So briefly on a number line, let's start here at 0. And let's do 5 times 2, which is 2 plus 2 plus 2 plus 2 plus 2. And so what we do is we do our repeated addition. 5 times. And that gets us to 10. I've heard this called skip counting. I don't know if you have heard of that. So we're counting by 2s. 2, 4, 6, 8, 10. The rectangle idea kind of breaks down when you're multiplying negative numbers, because what does a negative square look like? Right? And that's why this skip counting approach can be useful. If multiplication is repeated addition, now let's look at 4 times -3. Well, that's repeated addition of the -3. Oops. -3 plus -3 is -6, plus -3 is -9, plus -3 is -12. 4 times -3 is -12. And if I put this on a number line, I'm going to start 0 over here on the right because I'm adding negative numbers. And I'm going to add -3 to itself 4 times. 1, does that, no, that wasn't 3. 1, 2, 3, 4, and it gets me down to -12. I'm not going to mark all of them, but I'll mark those skip counting numbers. 4 sets of -3. The emphasis of this course is understanding why these are true. If you're asked to multiply 2 3-digit numbers together, we can do that by hand. I'm going to show you how to do it by hand, but calculators are fine, right? It's more that the idea is for you to understand how when you multiply a positive by a negative, you end up with a negative. -3 times 4, that's a little harder to visualize, right? I mean, what does it mean to take -3 sets of a number, or to take 4 steps -3 times, right? So this is harder to visualize, at least for me. But fortunately, it doesn't really matter because we can always switch that order. And now think about it as 4 steps of -3 instead of -3 steps of 4. Right? That's our associative property. When we're just doing a multiplication, I can think of it as -3 sets of 4 or as 4 sets of -3. And I just personally, until I get comfortable with the idea, I'm going to pick the one that I can actually visualize 4 steps of -3, like so. Which we know is -12. What's 4 times 3? 12. And when you make it a -3, we also have a -12. So let's write down our rules for the sign of multiplication. To decide the sign of a multiplication. Positive times a positive will always give you a positive. Example, 5 times 2 gives me +10. And I could think of that as the rectangle approach or the number line approach. A negative times a negative, a negative times a positive. Or if I write it the opposite order, that positive times a negative right? Either one of those will always give you a negative. And our example here was 4 times -3, which was -12. And there's one other possibility, which is a negative times a negative. This will always give you a positive. I think honestly, it's easiest just to memorize these rules. Positive times a positive is a positive. Positive times a negative is a negative. And a negative times a negative is a positive. So an example here might be -6 times -7, which is +42. This is our rules for multiplying integers. The one the book says is 2 numbers with different signs will always have a negative product. I think it's easier to think of it as actually a negative times a positive or a positive times a negative. 2 numbers with the same sign, like a positive and a positive, or a negative and a negative, will always give you positive. And then there's an absolute value rule, but that just says absolute values always end up making things positive. And so I don't actually feel the need to write that down. That's somewhere else in our notes. Well, I'll write down absolute value signs. Symbols, not signs. Let me write that again. I didn't write the whole phrase anyway. Absolute value symbols always make the inside positive. So if, for example, the absolute value of 8 times -3 is the absolute value of -24, which is 24. Right? Absolute value symbols always make the inside positive. And you can write that as a little multiplication thing, but I don't really think that's necessary. It's in the book. These are our 3 critical ideas to remember when you're deciding the sign of a multiplication. I'm glad I checked the book because the book used a word and that word is product. Now, in general English, product means just the result of doing something, right? If I've got a couple of slices of bread and some deli meat, some vegetables and some spread, I put them all together, the product is a sandwich, right? If I've got some carne asada and some tortillas, some salsa, cebolla, cilantro, put them all together, the product is a taco. Yeah. In math, product always means the result of a multiplication. It never is the product of adding numbers together, or the product of subtracting, or the product of dividing. It's always the result of a multiplication. So when the book says 2 numbers with different signs will always have a negative product, what it means is if you multiply a negative times a positive, the product will be negative. The result of that multiplication will be negative. And one other thing, the book calls it the anti-identity, but any number times -1 will change its sign. This is pretty useful, actually, because very often we want to change the sign of a number. And all we have to do is multiply it by -1. So for example, 4 times -1 is -4. And -2 times -1 is +2. Any number times -1 will change its sign. And that actually comes up more often when we're working with algebra, and we have to distribute multiplication through parentheses, which I don't know if we've done yet. Those folks watching on the video, I'm just paging back to see if I can remember. No, we haven't done that. My audio is on. The folks online can hear me. That one's off, or else I get feedback. But thanks, Jesse. Okay, so yeah, here are kind of our important rules that we're going to remember. So we're ready to go to division. Division, the counterpart to multiplication. And we're going to do just integers. We're going to stay in the integers for this section of the book. I will probably actually expand upon that a little bit, but the rules are the same. So a positive divided by a positive will be positive. An example, 28, which is positive, divided by 4, which is positive, equals 7, which is positive. A positive divided by a negative, or switch them, a negative divided by a positive. All right, that's the counterpart to multiplying two things that have different sign, will be negative. Example, let's do 36 divided by -9. 36 divided by 9 is 4, so 36 divided by -9 equals -4. Or I could do -50 divided by +10, and that's going to be -5. So a positive divided by a negative will be negative, and also a negative divided by a positive will be negative. I want to draw your attention to where all these negative signs are. Notice in the first example, 36 over -9, the negative is in the denominator. And in the second, the negative is in the numerator. I might have to write down some more definitions. But it doesn't matter. So often we rewrite, spell that, 36 over -9, I just put the negative in front of everything and call it negative 36 over 9. Because negative 36 over 9 is like taking 36 divided by 9 and then making it negative, which is -4. So frequently when our denominator is negative, we just make the fraction itself a negative.
That's okay, right?
That's okay, yeah. We'll pull that negative out in front of everything. Or even if it's the numerator that's negative, we often, should this be a 10? That should be a 10. We often just pull that out and make the fraction itself a negative. That comes from, I would say, generally mathematical preference, laziness plus preference. It's easier just to always have the negative in front, and so we kind of always do that. Okay. Now there's two more rules for division. The first one is also analogous to the multiplication. A negative divided by a negative will be negative. So for example, let's do negative 32 divided by -4. That's going to be +8. And we often cancel the negatives as a little visual reminder. So if I happen to have just two terms, one on top and one on bottom, and they're both negatives, this is one of those times when you're going to want to watch as a video as opposed to a photo. So I will wait. And as soon as you're done writing your notes, please look up when you're done. No hurry. Okay. Say. Okay. Just make those both positive. All right. We often cancel that way. And then we just write it as a positive over a positive. I will often do that. We can do that also with multiplication, but I think it's a little less likely to confuse ourselves when we do it with division because of where those plus and minus signs are living. Okay. Those are our, oh, one more. Yep. You cannot divide by 0. Example, 7 divided by 0 is undefined. And also -3 by 0 divided by 0 is undefined. So we add that extra rule just to remind ourselves. Technically, there's a multiplication rule as well, which is any number times 0 equals 0. I'll add this to the bottom just for our notes. So that's going to be on your notes. Any number times 0 equals 0, but you cannot divide by 0. All right. So that covers the multiplication and division. Let's take another look at exponential notation. which, if you remember, is repeated multiplication. So something like 4 to the third power or 4 to the 3 is just a compact way of writing 4 times 4 times 4, which is 64. And this works on negative numbers as well. So let's look at -3 raised to the 5th power. And this is how I recommend you develop your intuition for these ideas, is you actually write it out. -3 times -3 times -3 times -3 times -3. And we can build this up as we go, working left to right because it's all multiplication. What's -3 times -3? Positive now, 9, because a negative times a negative is a positive. So we've collapsed that first -3 times -3 into 9. And we're going to continue working left to right. 9 times -3. Positive or negative?
Positive. Or negative.
Negative. 9 times -3. A positive times a negative is going to be a negative. And I'll help with the arithmetic for these ones. -27 times -3. Is that going to be positive or negative?
Positive.
Positive, because a negative times a negative is a positive. That's 81 times -3. And 81 times -3, is that going to be positive or negative? Negative. It's -243. Negative numbers raised to odd powers or odd exponents will give you a negative result. -3 raised to the 5th is -243. That's one of our rules. Let's do another example. This one a little shorter. -2 raised to the 3rd power. That's a negative number on the inside, and the power is odd. It doesn't matter if what's inside is odd or even, it just has to be negative. All right, so this is negative. The base is negative. The power is odd. If I write out what that repeated multiplication is, I have -2 times -2 times -2. The -2 times -2 is a +4. 4 times -2 is -8. Starts odd, ends odd. And the reason for that is because of what it means to do exponentials. Okay. Negative numbers raised to even powers will give you a positive result. So it's different here. But again, it comes from the rules of exponentials. Let's start with a very simple example. -4, okay, that's negative. But I'm gonna square it, which is an even power. That's -4 times -4. A negative times a negative is a positive, so it's positive 16. Okay. Another example, we can do one a little bit longer. Let's look at -7 raised to the 6th power. And again, I'm going to write out what I have. And I can't do all of this in my head, but I know the first couple. -7 times -7 is positive 49. Times -7 is negative 343. Times. Multiply that again. I'm going to get negative times a negative, which is a positive 2401. Times -7 times -7. I'll squeeze the last two on the same line. Next multiplication is going to give me a negative 16807 times a -7, but a negative times a negative is a positive. I'm going to end up with positive 117,649. Negative number to start, but it's an even power, gives me a positive number as a result. Also, exponentials grow super duper fast, right? Especially compared to just multiplication or repeated addition. Repeated multiplication grows super, super fast. This is why we say things are growing exponentially. In colloquial language, what we mean is they're growing super fast. In mathematics, it's very specific, but it also means it ends up growing super fast. All right. Now, this second rule has a very important consequence. And it's highlighted in the book, which I like. Warning, -2 to the 4th is not the same as negative of 2 to the 4th. So again, that sounded like I said the exact same thing, and that's why our notation is super important. If your negative is inside of parentheses, it's not the same thing as if your negative is, if there is no parentheses, because of PEMDAS. We do exponentials before we do multiplication. That minus is like the multiplying by -1. So we would do the 2 to the 4th and then the minus. Where over here, and again, I really like it if you write out what this means. That's -2 times -2 times -2 times -2 on the left. But on the right, that minus is not part of the base because of PEMDAS. So it's just -2 times 2 times 2 times 2. If you work down the left side, you have it raised to an even power. So that is going to end up being positive 16. But on the right side, it's going to be negative times 16, a negative of a 16. So the parentheses are super important when you're doing exponentials, when you're doing powers. All right. Anybody have questions about that? So now that we introduce negatives with the with our multiplication and addition, I just want to show you one example of how you would approach an order of operations question. And this is number 45 from the book. And we're going to simplify negative 12 times negative 5 plus negative 11 with a bunch of parentheses. And then I divide all of that by negative 8. So we're going to have to use what we remember about adding and subtracting integers as well as multiplying and dividing by integers. Right, here's one of those places where it's much easier to track the math as a picture than as a video, which is good. I'll try to highlight when it's video math instead of picture math. All right, order of operations. What comes first? Parentheses. So I've got these pieces in my parentheses. That minus 11 in parentheses is mostly there as a visual cue that I'm taking a negative and I'm adding a negative. So we could go back to our rules for addition and subtraction of integers and realize a minus plus a negative is like a minus minus the number. Right, that's one of our rules of addition and subtraction for integers. Rules of plus and minus for integers. And the benefit of that is it kind of simplifies what we're looking at. Adding a negative number is like subtracting the positive version of that number. And I still have parentheses. So I'm going to do these parentheses next. Minus 5 minus 11 is negative 16. Because we start at negative 5 and we walk another step, 11 steps to the left. And then multiply it by negative 12 and divide it by negative 8. I copied the question exactly as written. Hold on, let me do this first. This is our PEMDAS here. I copied the question exactly as written, but this might be one of those times when you use parentheses that aren't strictly necessary, but can be useful. Because I can remind myself that technically there's a parentheses, or I could put a parentheses around that, which can help me as I'm doing the multiplication. So I have negative 12 times negative 16 divided by negative 8. What comes next in PEMDAS? Multiplication. Yeah, comes before division. Yeah, which is good because that reinforces that not only does multiplication come before division, but this vertical division implies that you do the top and you do the bottom before you do the division. So really it should be put BEMDAS, right? That's really what it should be, because when you have a division, you do the top and the bottom before you move on with the other things. Negative 12 times negative 16. What's a negative times a negative? It's going to be a positive. Great. Let's see if I can do this in my head. 48 times 3, 100. Yeah, that's what I thought. It's 144, and it's going to be positive. And we're going to divide it by a negative 8. multiplying a negative times a negative equals positive. 144 divided by -8, is it gonna be positive or negative?
You get 144 12 times,
Yes. Did I do it right?
192 is.
Oh, thank you. Bad arithmetic,
Is a little confused.
as you should be. Oh, yeah, of course. Of course, it wasn't the other one. Okay, 192 over -8. And I'm not gonna take any risks. 192 divided by -8, is that gonna be a positive or a negative? Negative. And remember, we often just write it as the negative of the fraction. -24. That's how you walk through the PEMDAS simplification when now you're adding, subtracting, multiplying, and dividing with positive and negative. In fact, those were all negative integers. I just started by adding a negative integer. Okay. All right, this brings us to 2.4. Solving multi-step equations. We've solved a couple of equations so far. We've solved them with just an addition. And remember, we still want to isolate the variable. So we can just subtract the 7 from both sides. And the reason I subtract is because subtraction undoes addition. And I get x on the left side and 12 on the right side, and now I'm done. And we've done other examples like 39 equals 13x. And again, I want to isolate the variable without any multiplication. If we want to undo multiplication, what operation do we use? Division. So I'm going to divide both sides by that multiple on x that I don't want. Divide both sides by 13. And 13 divided by 13 cancels to become 1. And so I have x on the right side, and 39 over 13 is 3. So now 3 equals x, which is the same as x equals 3, and I'm done. One more review example. And this one I'm going to solve in 2 different ways. 10 minus x equals 18. Let's do that one. And let's solve it 2 different ways. First way here and the second way there. So the first way is how we solved it before, and that says we want x not only by itself, but also positive. So maybe the first thing to do is figure out how to get a positive x in there instead of a negative x. And I think the easiest way to do that is to add x to both sides, which I can do because x is a number. Whatever that number is, I can add it to both sides. Minus x plus x cancels to be 0. and then the positive x on the other side. These are all fact families, and we build fact families by doing mathematically legal operations. And now I've turned it back into something like my first equation. Instead of x plus 7 equals 19, it's 10 equal 18 plus x. But for example, if I read it backward, it looked basically the same. So how do I isolate the x? I'll subtract 18 from both sides. That gives me x by itself on the right and negative 8 on the left. That's one way to solve it. The other way would be to say, I'm not going to worry so much right now that that x is negative. I'm going to prioritize getting it by itself. And to do that, I can subtract 10 from both sides. And I get negative x equals 8, because 18 minus 10 is 8. Unfortunately, I haven't figured out what x is. I figured out what the opposite of x is. And maybe from here you can jump and straight to say, okay, if negative x is 8, then positive x has to equal negative 8. But really what we're doing is we're taking this negative x and we multiply it by negative 1. So if we multiply by a negative 1 on both sides, remember any number times negative 1 changes the sign. So negative x turns into positive x, and positive 8 turns into negative 8. Option 1 works just fine using the tools we developed last week. Option 2 works just fine using one of those tools that we developed today, where you multiply any number by negative 1 and you change the sign. And mathematically, you have to do that on both sides. Anybody have questions about that? Okay. So let's do a two-step equation. Using integers. Can't remember. I think we've done some of these before. It's been a long term already. Yeah, let me see. 1.5. No, actually we haven't, which is fine. So a two-step equation might involve addition or subtraction, and also multiplication or division. So it could look something like 2x plus 7 equals 35. There's an addition and there's also a multiplication. And here's the thing about solving multi-step equations. PEMDAS is how we do order of operations. But for solving, we work backwards. So I like to think of it as a mirror. And if I were to write this using our normal ones, it's SADMAP. So for basic two-step equations, we use a SADMAP process. We undo subtraction and addition or addition first, and then we undo multiplication or division. And usually in these two-step processes, we don't have exponents, but we could, or parentheses, just like with PEMDAS, parentheses get pretty tricky. But if it's a super straightforward then yes, we do the parentheses last. So for a basic two-step equation that involves addition or subtraction and also multiplication or division, we SADMAP to undo. All right. Let's grab that equation. Start over fresh at the top of this page. So our example was 2x plus 7 equals 35. And to solve this equation, we're going to undo the operations using SADMAP. So which operation do we undo first? The addition, because undoing addition comes before undoing multiplication. And to undo addition, we can just subtract 7 from both sides. And we have 2x equals 28. And then how do we undo the multiplication? Divide both sides by 2. And we get x equals 14. And we're done. And we can check in our original equation, 2 times 14 plus 7. Now we're moving forward, so we do PEMDAS, right? We're evaluating, so we do the multiplication first. 28 plus 7 equals 35. Okay. Let's do another example. 3x minus 10 equals 71. We're trying to solve. I really should be writing solve. Because we can do different things with equations. Here we're solving them. We're trying to solve 3x minus 10 equals 81. So what operation do we undo first? Subtraction, because subtraction comes before multiplication. And we'll undo it by adding 10 to both sides. That gives us 3x on the left and 81 on the right, because 71 plus 10 is 81. And how do we isolate the x? Right, we divide because division undoes multiplication. And we get that x equals 27. We have solved it. And now we check it. 3 times 27 and then minus 10 is 81 minus 10, which is 71. The hardest thing to do in math is check your answers, because for humans, as soon as our brain gets something that we think is right, our brain will always try to convince us that it was right, even if it was wrong at the beginning. That's called confirmation bias. So if I had put 25 for x, I probably would have said that 3 times 25 equals 81, even though it doesn't. But that's because my brain wants to say the things I did were right, and it tries to convince you. So checking your work is actually a pretty challenging part because it goes against how our brains like to do things. Couple more examples. Let's do 14 minus 5x equals, I think I can do this. Okay, if I did 56, I'm gonna need to, in order to do a decent question, I gotta do a little bit of work. Okay, -1. Yeah, that'll work. Even though I showed you two different ways to do it, right? Let's work with some consistency when we can to build those skills. And let's work through SADMAP. But it's a little tricky here. Which one of these am I going to try to undo? The -5, because it's a subtraction? Well, the problem is it's not actually a subtraction, it's a multiplication. So if I am going to do a subtraction, I have to subtract everything, the -5x, to move the whole thing on the other side. And technically, that's not really the SADMAP process, because I want to isolate the x, so I need to get rid of the 14 first. Now, if you subtract 5x from both sides, that'll work. But you cannot just subtract 5 to get rid of it because it's multiplied by the x. So instead, I'm going to think of that 14 as, aha, that's being added in. That's a positive 14 that's being added in. So that's my addition part of SADMAP. So the first thing I'm going to do is I'm going to subtract 14 from both sides, which gives me -5x on the left and -15 on the right. And now I have a multiplication. Even though there's a minus sign, what it's telling me is I'm multiplying x times -5. So again, I can't just get rid of that -5 by adding a positive 5 to it because there's a multiplication here. How do I get rid of multiplication? Division. So now I'll divide by -5 on both sides. -5 divided by -5 gives me the x, and -15 divided by -5, it should be a positive, so it should give me +3. And let's check. Try to forget all the other work you did and just go back to the very original equation. 14 minus 5 times 3 is 14 minus 15, and that's the -1 that it had to give. Right, so the complexity of the equations can be a lot bigger, and you have to kind of be more careful and more systematic when you decide what operations am I going to undo. All right, let's do one with division, and then I'll hand the worksheets out. X over 3 minus 2 equals 4. We can use SADMAP on this, no problem. What am I going to take care of first? The subtraction, so I can counter that by adding 2 to both sides. And I'm going to get x over 3 equals 6. And what operation am I going to undo next? Division. So to undo division, I use multiplication. I'll multiply both sides by 3. And I get x equals 18. And I can check that. 18 over 3 minus 2 is 6 minus 2, which is 4. Yes. And again, if I had gotten the wrong number, I can almost guarantee you, like if I had gotten 24, I would have tried to convince you that 24 divided by 3 equals 6. So it's hard to do the checking. One of the challenges with division though, remember how like PEMDAS has all these exceptions? So does SADMAP. Because if I had written x minus 2 and then all of it divided by 3, that's a different question. Equals 4. This is a different question. If I tried to add 2 to both sides here, I wouldn't be isolating the x anymore because the x is trapped inside a division. So there are two ways to approach this. One is you can say, I don't like this division. I'm going to break it into 2 pieces. But the more common way is to say, I don't like everything over a fraction. So undo, I'm going to call it a total fraction. Undo total fractions first. So maybe it should be FASADMAP. Right, undo total fractions first. Hi, Ossie. So if I undo this total fraction divided by 3, how do I undo that? Well, this total fraction, that's a division. So to undo this total division, I have to actually do a total multiplication. So I have to take 3 times that fraction, x minus 2 over 3 equals 4 times 3. And that 3 times cancels with the total fraction 3. And it gives me x minus 2 equals 12. And now I'm going to add 2 to both sides, and I get x equals 14, which is very different than x equals 18. Right? Just like with PEMDAS, those total fractions change the way you think about your order of operation. We have the top-bottom piece. It also changes it when we're solving. And it takes practice to recognize. I can tell you that if it's a fraction just with the x part, then you do SADPET normally. But if it's a total fraction, then you have to undo the total fraction first. And if you want those reminders, that's why we're here, right? Your neighbors and us is like, okay, which one do I do first? And we'll go through it, and that repetition will help you remember those rules and order. Okay, let me stop the recording and I'll hand out the worksheets.